on the torque equations, the maximum torque and the starting torque. Okay, some more equations we'll be looking, some more problems we'll be looking once we go through the various aspects of machines again. Okay, so next we'll look into the relation between torque and slip, which is very important in assessing and selecting a particular machine for a particular operation. Okay. So next point what we see is relation between torque and slip. So here we have torque, running torque, especially because slip will come into picture only in running torque when the motor starts running. So we have T is equals to, I can write here it as K into 5, okay, S E2 R2 divided by R2 square plus S X2 square. Okay. So this can also be written as, I can write this as K1 E2 square S into R2, yes should come first, R2 square plus S X2 whole square, both equations are same. Okay. One thing we should observe here, slip is not a constant value throughout the operation of the induction motor. Okay. Slip is not a constant value throughout the operation of the induction motor. Okay. Slip will change when the load will change. However small or large the load variation may be, the slip will definitely change. Hence, the load variation on the induction motor is recognized by variation in its slip. Okay? And the slip value is too low when the machine is at no load. The slip value will be having considerable value when the machine may be at full load. Because speed drops, slip increases. Okay, if the speed is more, slip is less. If the slip is more, if the speed is less, slip is more. Okay, so the no load slip is almost equals to 0. Okay, the no load slip is almost equals to 0. Please remember, slip S is equals to ns minus n divided by ns. So at standstill, slip is 1. At no load operation, the slip is nearly 0. So these 2 points you should be always keeping in mind. Okay, so at standstill, n is equals to 0, s is equals to 1. At no load operation, n is nearly equal to ns and slip is nearly equal to 0. It is very low value, hardly 1%, 2% slip we will get. Okay, so it is very low value at no load condition and it is 1 at standstill condition. Okay, and from no load to full load, the variation of slip is considerable value. Therefore, the behavior of the torque with respect to slip is different at different values of the slip. The behavior of the torque with respect to slip is different at different values of the slip. So, first let me plot a graph. So this is say torque. Okay. And let me take this x-axis. It can be relation between torque and slip and also speed. because slip is found in terms of speed. Okay. So as the speed increases, let this be slip. Okay. And let this be one more axis, which is speed. This is speed. Okay. So initially the speed is 0. Okay. Then speed may be 1 here. Speed uh, percentage of ns, that is n divided by ns. It is just for the sake of representation. Okay. Percentage of ns I am expressing. Okay. Now it may be like this: 0.2, 0.4, 0.6, 0.8. Okay. So when speed is 0, slip is 1. When speed is ns, slip is 0. So if speed is varying towards right, increasing towards right, slip will be increasing towards left. So at 80% of the speed, the slip will be 20%. At 60% of the speed, the slip will be 40%. At 40% of the speed, the slip will be 60%. At 20% of the speed, the slip will be 80%. At 0% of the speed, the slip will be 100%. Okay. It is a different kind of characteristic in the sense the representation is slightly different. The representation is slightly different. That's it. Now, when the speed is high, I will start the machine at no load condition. I have to see the machine from no load condition. Okay. So when machine is at no load, when a machine is at no load, the running torque developed. Sorry. When ns is equals to n is equals to ns, the slip is 0. Therefore, torque is 0. At s is equals to 0, my tr is equals to 0 because s is there in the numerator of the equation. Therefore, the torque developed becomes 0. Okay. What does this mean physically? When speed equals ns, when do we get slip 0? When n becomes equal to ns, slip becomes 0. Okay. So what does this mean, n becoming ns? The rotor has caught the synchronous speed. When the rotor has caught the synchronous speed, the relative speed between the RMF and the conductor is 0. It means the conductor is not cutting any flux. Therefore, the EMF induced in the conductor is 0, current in the conductor is 0, hence the torque developed is 0, speed is 0. Motor will not run. It is that condition. Okay. So it is this condition where n is equals to ns. When n is equals to ns, the rotor will stop. It means the torque developed is 0. So the torque developed is 0. Now as the speed decreases from ns, okay, as the speed decreases from ns, the value of slip is very low. It is rising from 0. The value of slip is very low. Okay. So if you observe here TR, okay, K1 is a constant, E2 depends upon supply voltage is a constant. Okay. This TR is now proportional to S into R2 divided by R2 square plus S X2 square. S into R2 divided by R2 square plus S into X2 square. Now here at lower values of slip, yes, that is N nearly equal to Ns. At lower values of slip, S, my S into X2 and its square is much less than R2 square. Is much less than R2 square. Therefore, R2 square plus S X2 whole square is nearly equal to R2 square. It means I can neglect S into X2 its square. Therefore, I can write TR is proportional to S into R2 divided by R2 square, or TR is equals to, or TR proportional to S divided by R2. S divided by R2. Now we know once the machine starts operating, R2 is constant. Okay. Once motor starts, R2 is nearly constant. Therefore, my running torque TR is directly proportional to slip S. Okay. So TR is directly proportional to slip S. And one thing we should remember, the torque should never be crossing the maximum torque line. So this is the maximum torque, T max. Okay. Maximum torque. So it is very much clear from, you take this as equation 1, or equation 2 you take. Let me take this as equation 1. Okay. So torque is proportional to slip. Now the question is torque always proportional to slip? Okay. So we should think that, is the torque always proportional to slip? Okay. No doubt here it is obtained torque is proportional to slip. But will this relation be forever throughout the operation of the slip? Okay. So as the slip increases from 0 to 1, as the slip increases from 0 to 1, the torque also increases from 0 to 1, or from 0 to T max. We can observe here. As slip increases, okay, the torque also increases. The torque also increases until it becomes maximum. Also increases till maximum torque value. Till maximum torque value. Okay, and maximum torque occurs at slip is equals to R2 by X2. Maximum torque occurs, okay, at S is equals to R2 by X2. Okay. So this maximum torque is known as pull-out torque or breakdown torque. Sometimes it is also known as stalling torque. Okay. Now, when the slip further increases beyond this breakdown slip, okay, this is also known as pull-out slip, breakdown slip, or stalling slip. When the slip increases beyond maximum torque, uh, as slip increases, beyond maximum torque, my S into X2 becomes greater than R2. My S into X2 becomes greater than R2. Therefore, S into X2 square is greater than R2 square, and R2 can be neglected. And R2 can be neglected. Okay. Therefore, R from equation 1, my TR is now proportional to, so here it is proportional to S into R2 divided by R2 square plus S into X2 square we have, na? R2 square plus S into X2 square. Okay. So this I will write this as TR proportional to S into R2 divided by S into X2 square. S square, sorry. S into X2 square. Okay. Now R2 is a constant, we know that. Okay. R2 is a constant. Okay. Therefore, TR is proportional to, okay, S divided by S square into X2 square, or TR proportional to 1 over S into X2 square. Now what is X2? Okay, or I can write TR proportional to 1 over S, because X2 is a standstill reactance which is also a constant. S into X2 is variable, but X2 is a constant as it is a standstill reactance. Okay. Now, this is one more relation. We take this as equation 3. As per equation 2, the torque is directly proportional to slip. As per equation 3, the torque is inversely proportional to slip. Okay. Now, how this is drawn? Torque is directly proportional to slip until it reaches maximum value. Once torque reaches maximum value, beyond maximum torque value, the torque is inversely proportional to slip. Okay. So what we can observe here from equation 2 and 3, from equation 2 and 3, we observe that we observe that torque torque is directly proportional to slip till it reaches maximum torque value. Okay, and is inversely proportional to slip beyond maximum torque value. Beyond maximum torque value. So now we will draw this curve. Okay. Okay. So as slip is increasing from right side to left side, I am taking the reference as a slip because slip is there in the equation of torque. So as the slip increases, the torque is increasing linearly. Once it reaches maximum value, okay, the torque is decreasing. Okay, so this is for the rotor resistance R2. Okay, so this is the speed torque curve or speed torque characteristic of a DC motor. Speed torque characteristic of a DC motor. So till okay, till the torque reaches its maximum value, the torque varies linearly with slip, and this is the desirable region of operation of motor. Stable region of operation. What happens beyond this maximum torque point is if the slip is varied beyond the maximum torque, then the motor speed will decrease. Slip is increasing means speed is decreasing. See, the speed here is almost zero. Okay, the speed here is almost zero. So beyond certain point, after the speed decreases, the motor will stop. Okay, because the torque is increasing and it is decreasing. If the torque decreases below certain value, below which it cannot supply the rotational losses requirement, then the motor will stop. So generally, the stable region of operation of motor is always when the torque is linearly varying with the slip, but it is below the maximum torque value. It is below the maximum torque value. Okay, so this is the stable region of operation. So from equation 1 and 2, and even from equation 3, we observe the rotor resistance has no role to play in the running torque. Yes, the maximum torque is not decided by the rotor resistance. Maximum torque is fixed. Okay, maximum torque is fixed. But what we have here, the rotor resistance R2, okay, will not decide will not decide the maximum torque, as Tmax is independent of R2. As Tmax is independent of R2. But the slip at which Tmax occurs is decided by R2, because SB is equals to R2 by X2. This is what? Slip at Tmax. So the value of slip at which the maximum torque occurs is decided by R2, but not the value of maximum torque. The value of maximum torque is independent of R2, but the point of operation at which the maximum torque should occur is decided by the rotor resistance. Now, if R2 is high, SB is also high, and vice versa. Okay, so SB is directly proportional to R2. Now this is one value of R2 with which I got this curve. Now if I double the R2, okay, if I double the R2, what will happen? The value of torque will not change. I will take some different color. Okay, the value of torque will not change, but the point at which the maximum torque occurs will change. The slip at which maximum torque occurs will change. So here if you observe, the slip at which maximum torque is occurring is nearly 0.3, okay, or 0.25. The slip at which maximum torque is occurring is 0.25. Now if I double the R2, then it will be more than 0.25. Okay, so here what will happen? The curve will be still linear. It may be 2 or 2. But the point at which maximum torque is occurring, the same maximum torque value is occurring, it will increase. So it may be 0.42 or 0.45. If I further increase R2, if I further increase R2, okay, the value of slip at which maximum torque occurs will further increase. Now, if I further increase R2, R2 of much greater value. Okay, so this is the torque slip characteristic of a induction motor. Torque slip characteristic of an induction motor varying with respect to slip. Okay. Now, for any value of R2, this region is more stable for operation because maximum torque occurs in a very lesser value of slip. Okay, and we will get a wide range of operation of the slip values. The speed will also not drop because induction motor is operating at with the applications which demand various values of speed. Say for example, if you are using an induction motor as a water pump, okay, uh, the speed of operation is totally different. Now suppose you are using the induction motor as a drive system for a what we can say escalator in the malls and shopping complexes. We have in the lifts in our college, all these are using induction motors only, three-phase induction motors. Now can I expect very large speeds or moderate speeds or low speeds? If you have to design the induction motor drive for a lift operation, what speeds you will keep? You keep more speed less torque, or less torque more torque less speed?
More torque.
Yes, there you want more torque or more speed?
More torque.
More torque we need because I cannot operate the lift at very large speeds, or else people will die of heart attack. Okay, so there the position of the curve which is satisfying the maximum torque will be different. So accordingly, I have to choose this value of R2. Okay, so this is very, very important to remember and understand how exactly the torque is varying with respect to slip. So this is one of the very important point that you should always remember throughout your electrical career. Okay, that how an induction motor varies with slip. If you are into the career of motors, this you have to remember compulsorily. Okay, compulsorily you should remember this. Okay, and this is one of the very important point in the entire operation of induction motor, torque slip characteristics. Okay, so I will repeat it once again. So this torque is having equation K1 E2 square S R2 R2 square plus S X2 square. If I take out all the constant values, the torque is proportional to S into R2 divided by R2 square plus S X2 square. Now when the slip is at lower value, okay, when the slip is at lower value, in the sense when the motor is at no load, okay, the motor is at lower here, at lower values of slip means what? That is motor at no load. Okay, so at lower values of slip, my S into R2 square, S into X2 square will be much lesser than S R2 square. Therefore, we will neglect this term, and my torque will become proportional to S divided by R2, or as R2 is almost a constant, my torque is directly proportional to slip. Okay, so with this relation, the torque will increase with respect to slip linearly. The torque will increase with respect to slip linearly, and then it will reach the maximum torque value. Once the maximum torque value is obtained, my slip becomes S is equals to R2 by X2. Okay, and beyond maximum torque point, my S into X2 will be greater than R2. Okay, so initially the reactance is less, resistance is more. In the later stage, resistance is less, reactance is more. Okay, so my S into X2 is greater than R2. Therefore, my torque is now inversely proportional to the slip. The torque will be now inversely proportional to the slip. Okay, and the torque starts decreasing once it reaches the maximum value. Okay, once it reaches the maximum value. Okay, so with this we can observe the speed torque curve is, or the torque slip curve is increasing linearly till maximum torque, and beyond that point it is decreasing. Okay, the value of maximum torque may not be decided by the rotor resistance R2, but the point at which maximum torque occurs is decided by the R2. So if I vary the R2, if I keep the larger values of R2, then the slip at which the maximum torque occurs will also increase. So with that, I can get a set of curves with respect to the values of R2. So if I change R2, the characteristic will change. If I change R2, the characteristic will change. Okay. So with this, I can get a set of curves to study and use the particular motor for a particular application. Okay. Is it clear?
Yes.
Yes, sir.
Any doubts?
No.
So next we will see effect of change in supply voltage on torque and speed. Effect of change in supply voltage on torque and speed. Okay. So we have T is equals to, or TR is equals to K phi S into E2 R2 square. Sorry, it is R2, not R2 square, divided by R2 square plus S into X2 square. This equation we have. Now we know this, sorry, it is not E2 square, it is E2. If I take phi, it is E2. Okay? If I don't take phi, it is E2 square. Or this I can write this as K1 S E2 square R2 divided by R2 square plus S into X2 whole square. Okay. Now, so here E2 is proportional to, so V. E2 is proportional to V. Why it is proportional to V? Because E2 is proportional to the stator flux. Always. Induced EMF is always proportional to the flux which is inducing it. Okay, so E2 is proportional to stator flux, and stator flux is proportional to supply voltage. Okay, therefore E2 is proportional to supply voltage. Okay, E2 is proportional to supply voltage. Therefore, I can say my TR is proportional to V square. The starting torque was also proportional to V square. Okay. So what we can see here is TR is very sensitive towards change in supply voltage. Towards change in supply voltage. Towards change supply voltage. I have told TR proportional to V square doesn't mean that torque is proportional to 400 square. Okay, supply voltage is 400. Torque is not proportional to 400 square. You cannot take TR is equals to say some constant C into V square. You can't do that. Here we are studying how the torque is varying with respect to variation in voltage, rather than how the torque is directly depending upon the voltage. That is not the issue here that we are seeing. Okay, that you should understand. Okay, so therefore, uh, if torque varies, or if supply voltage varies, if supply voltage varies, the torque varies square times. The torque varies square times. Okay, the torque varies square times. So uh, it is proportional to S into V square, not only V square, because it is running torque. If it was starting torque, S was 1. The torque is proportional to S into V square. Okay. So when we are varying the supply voltage, we should be careful enough, okay, that the small variations will also result in the large deviation in the torque values. And generally, when the motors are connected to the standard grid supply, the variation of input voltage may not be that much. But when the induction motors may be operating with a dedicated supply, like the diesel generator, what we will be having in the shopping complex or in the housing complex. Suppose it is operating, the motor is operating with the lift. In the lift, you can observe, okay, you can observe the lift operation will not be the same when it was with grid supply and when it was with the generator supply. Okay. uh, Even when if you observe in your house, the fan what we use is an induction motor. Okay, single phase induction motor, ceiling fan. If you observe, when there is a electricity supply from the board, the fan will be running with almost lesser noise or no noise. But when you turn on the inverter when the supply is cut off, the fan will make some amount of humming noise. The reasons are different. Okay, because the output of inverter may not be constant all the time, though we use voltage regulators there, but may not be constant all the time because of harmonics, because of so many things, the output will change. So the behavior of induction motor is very sensitive towards these supply changes. That is what I want to mention. Okay. So if supply voltage decreases, then torque also decreases. Okay, but when the uh, torque decreases, speed will also vary and slip will also vary. Okay, that is there. Okay, so now here, if we want, okay, if torque has to be maintained constant, if torque to be kept constant, if torque to be kept constant, okay, then then slip increases with decrease in supply. Slip increases with the decrease in supply voltage. That is obviously what happens. When the supply voltage decreases, speed decreases. Therefore, slip increases. Okay. So let us see. Let supply voltage V uh, change to V dash. Slip yes, change to S dash. Okay. then torque TR change to TR dash. Okay. Now, if I want TR dash and TR to be constant, let us take the ratio. Therefore, the ratio can be given as TR or TR divided by TR dash is equals to S into V square divided by S dash into V dash square. If I keep this ratio constant, my change in torque will not be there. This is a very important relation in control of induction motor. Okay, this is very important relation in control of induction motor. The best example I will give you for this kind of control, I will say, when we are using a elevator in the mall, we all visit malls in Bangalore. Okay, you check the speed of the elevator when nobody is there on that. You check the speed of the elevator when nobody is on that. So what is the torque requirement of the load? Is it minimum or maximum?
Minimum.
Minimum. Now suppose some 10 members will climb up the elevator. What will be the torque requirement?
More.
Increased. But did you observe the speed? Had you observed the speed there, the speed of the elevator will not change. The speed of the elevator will not change. When nobody is there, elevator will not run with a large speed. Okay? When many are there, elevator will not run with a slow speed. Okay? Whether there is nobody, whether there are 10 members or whether there are 50 members on the elevator steps, the speed of the elevator is always constant. So what they are balancing? They are actually balancing the slip so that the torque developed at all the points is constant. Because supply voltage is constant, I can't change supply voltage there, it is 415 volts. The torque requirement is constant. So what they are balancing there? Out of this relation, okay, torque required should be constant, voltage applied is constant. Now what is the only thing that I can balance?
Slip.
Is the slip. Did you observe this point? If not observed, anytime when you now see the elevator, observe this point. The elevator will always run at a constant speed. Whether there is one person or whether there are two person or whether there are 25 people on the elevator steps. It will always run at this constant speed because as the people increase on the elevator, the load torque requirement will increase, speed will decrease. Okay, therefore slip varies. So the variation in this slip in the controller mechanism, they are balancing in such a way that always the torque is remaining constant. The load torque is remaining constant. The load torque is not changing. Therefore, the speed is not changing. Getting my point?
Yes, sir.
Okay, so these are the real world examples where we can see everywhere. Okay, else what will happen? When the load falls, speed increases. When the load falls, speed automatically increases. Okay, but in the elevator, it is not happening so. Even in the lift, it is not happening so. You observe when you come to college, whether one person is there in the lift cabin or whether there are 9 persons there in the lift cabin, the speed at which lift cabin moves up and down is the same. It won't change because again they are balancing the slip. So in one of the previous class I had mentioned The load condition on the of the induction motor is decided by the slip value. Is decided by the slip value. So slip is one such important quantity or parameter in our consideration and calculation that it will decide the entire operation of induction motor. It will decide the entire operation of induction motor. Okay. So with this, I will end today's session. There is next point to be seen is effect of change in supply frequency and the relation between maximum torque and full load torque and maximum torque and starting torque. So that we will take up in next class. Okay. So next class will be at 2:45. Today at 2:45. Okay. And if possible, even tomorrow I will be taking the class. Okay, extra class. If possible, I will just inform you by tomorrow only. So don't leave the class, give the attendance.